All right, so this is 2003 Physics B exam, Form B, question number 5. It's a 10-pointer thermodynamic PV diagram. It says 1 mole of an ideal gas is taken around the cycle A to B to C to A, as shown on the diagram above. Letter A says calculate the temperature of the gas at point A. Well, in a lot of problems, we've been able to use the combined gas law, you know, the one that says PV over T equals PV over T. That's how you relate one point to another point. But if you look over here, in order to find temperature, I need the temperature at one other place, and I don't have that. So what I'm going to have to do, instead of using the combined gas law, is just use the ideal gas law, which is PV equals nRT. And I'm going to do this for point A, because I want to find the temperature at A. So what you plug in determines what you get out. So in this case, I know my pressure is 200, volume is 20, and once you plug that into your calculator, you end up with your correct answer, which is 481 Kelvin. All right, part B says calculate the net work done on the gas during one complete cycle. Well, if you want to find the work done during a complete cycle, the easiest thing to do is to find the area of this triangle, because the work is the area under the curve. So looking this, the equation for a triangle's area is 1/2 BH, 1/2, and if you look over here, our base is the difference between 20 and 60, which is 40, and our height is 200. And when you plug all this in, you end up with 4,000 joules. Now, the last thing you need to worry about is the sign. Is this going to be positive or negative work? And as I mentioned in 2 other problems, if your cycle goes counterclockwise, that's positive work. If your cycle goes in that direction, which is actually the same exact direction, if your cycle goes in the opposite direction, which would be clockwise, that would be negative work. Sorry, it's been a long day. So in this case, it is just 4,000 joules. You don't have to put the positive sign on there. All right, part C has 2 parts. It wants to know, is heat added to or removed from the gas during one complete cycle? And then it asks you to calculate whatever that value is. Okay, anytime you ever have to calculate Q, the only equation you're going to use is the first law equation. Now, this is something I'm going to have to explain in class quite a bit, but first of all, you know the total energy, this is reversible. Therefore, when you get back from A to B to C all the way back to A, the energy is the same. So U has got to be equal to 0. Q is what we're looking for. And I found out that my work was positive. And once again, that right there, this is going to be a bit of a sticking point. But we will clear it up. So right now, just bear with me. Which means Q is equal to negative work. Which means it was removed from the gas. And once again, it's this work by the system and by the surroundings and on the gas and on the surroundings. We're going to have to clear that up, and it's just going to take a couple examples. Part D says, after one complete cycle, is the internal energy of the gas greater than, less than, or the same as before? Well, in order to get part C correct, you had to say that the total internal energy has got to be exactly the same. Now, if you had to prove this, one way to do it would be and don't forget, this temperature is final temperature minus initial temperature. Well, since it ends up right back where it started at A with the same volume and the same pressure, the change in temperature is just 0, which means that your change in internal energy is 0 also. And the very last question is about entropy. It says, after one complete cycle, is the entropy of the gas greater, less, or the same as before? Now, this is not a real thing. This is an ideal gas in a perfectly reversible system. And we've said that everything is the same. Well, entropy is the disorder. Well, since it ends up exactly back at A without anything having to do any work on the system in order to get it there, well, that means that entropy is the same also. So you could justify like this. That would be one way to justify it. Now, once again, in the real world, so far as we found, entropy is always increasing, unless something does outside work. Well, in this case, it goes from A to B, B to C, and then C goes right back to A, but nothing is doing anything. It's just the gas working. So in this case, entropy would stay the same.